So Augustine places the Platonic forms, the mathematical objects, in the mind of God. He finds a home for them in the mind of God. And so I find that very beautiful. So you could think as mathematics is an expression of the divine thought, and
Right.
this divine thought governs the material world. And that, I think, is a very beautiful view that brings together Christian philosophy and science without any conflict.
I welcome our listeners and viewers to another episode of The Catholic Scientist. That's the podcast of the Society of Catholic Scientists. I'm Steve Barr, the president of the Society. Our vice president and our co-host, Dan Keebler, is not with us today, so I'm going to be doing this solo. We're very honored to have as our guest today Martin Nowak, who is a professor of mathematics and also a professor of biology at Harvard University. Martin has won many awards and honors from around the world for his achievements in research, which span a remarkable range of subjects from evolutionary biology to cancer research. Martin is also, I'm proud to say, a member of the Society of Catholic Scientists. He gave a wonderful talk at our 2024 conference on how evolution leads to God. And so we had him back to give a talk at our 2025 conference this June on how mathematics leads to God. And that will be the topic of our discussion today. There'll be another episode where Dan Keebler is going to talk to Martin about evolution and God. So, Martin, welcome to the show.
Thank you so much for having me. It's a great honor to be with you and with this wonderful society.
Okay, so I'd like to, maybe we should start with some biographical things, so people know a little bit more about you and who you are. So I didn't say, but you're a mathematical biologist, which many people might find, they might not know what that is. I mean, to most people, mathematics and biology seem like, polar opposites, very different things. So how did you get interested in, when you were young, in mathematics, and how did you get interested in science, and which came first? Did you start with an interest in mathematics and move to science, or the other way around?
So I grew up in Vienna, and the most formative time of my life was perhaps the fact that for 12 years I visited a Catholic school. It was the school of Albert the Great, Albertus Magnus.
Uh-huh.
So I was there for primary school, for middle school and high school all at once. And the amazing thing is, it was formative in the following sense. It was academically the most challenging environment that I ever experienced. And afterwards, everything was easy in comparison. So the university afterwards, or then going to Oxford or Princeton or Harvard, all of this was easy in comparison. The real challenge was actually this high school and our many, many exams and rigorous exams. And so, but in any case, at that high school, I didn't really understand the concept of a scientist. So I wanted to become a medical doctor. And only in the last year of my studies, I read a book that was called The Eighth Day of Creation. And the Eighth Day of Creation was the history of molecular biology. And that changed my mind. Somehow I realized, also one of the teachers told me without knowing what it meant, I'm a scientist. So I realized what I want to do is to understand the chemical foundation of life. So I did not enroll in medicine, I enrolled in biochemistry. So then I started with chemistry, with physical chemistry, with physics and everything, but we also had mathematics.
Right.
But really, the first illumination was in the physics class. The professor in front of the class performed a mechanical experiment, and then he said, in order to understand that experiment, we have to make a calculation. And that completely surprised me. And before this, I thought, mathematics really is something there to generate homework, and riddles for high school kids, or maybe to calculate numbers in finance. But in the natural sciences, I hadn't realized that. And then I realized mathematics was the language of physics. And then I was introduced to theoretical chemistry, and more I was fascinated by the role that mathematics played in the natural sciences. And very quickly, I wanted to become a theoretical chemist. And I did a diploma thesis with Peter Schuster on the mathematics of viruses, essentially. And then during my PhD thesis, I met the mathematics professor, Carl Sigmund, and I became a PhD student of mathematical biology.
I see. Well, it's kind of interesting. When I talk to a lot of ordinary people, they understand that math has to do with calculations and probably, as you say, with finance and accounting and money and stuff, but they're not so clear. I think most people don't really understand that mathematics has to do with the physical world around them. I find that that this is a big puzzle. In fact, I tell my wife, as far as driving the car, there are things about how you should drive and stuff that actually are mathematical problems, or what causes traffic jams and things like that. But a lot of people, that's very strange idea that math, as you say, that's all about doing long division and things that boring stuff like that. And what does it have to do with the real world? So you sort of got into both at the same time, or maybe science first and then a little bit into math.
Yeah, I was
Um,
fascinated by this idea that really the language of science is mathematics, and especially with a great history of success in physics. And
right.
so here we can of course also ask, how did that come about?
Yeah.
The interesting thing is that Plato and Aristotle held mathematics in very high regard. So for them, mathematical knowledge was of a different kind. It was kind of above practical knowledge,
Right.
but it was below an intuition of the forms themselves. And I think they would not have understood that it was the language of physics. They did not see it as the language of all of science, for sure. But then we have to wait much longer. And the person who is often quoted as the first person to believe in the physical implication of a mathematical calculation was Johannes Kepler.
Hmm.
Galileo, of course, said mathematics is the language of nature. But Kepler really believed in the physical reality of a mathematical equation. And then came really the great wave of success of mathematics in physics, which
Right.
is Newton. And I find this mind blowing. And in biology, it was slower. It took much longer for mathematics to really take hold in biology. And as you said, when I began in my career, when I was in Oxford, I often got the question, a mathematical biologist, what is this?
Mm.
How can that be? Biology is too complicated for mathematics.
Right.
But this question has now ceased. So in the last 10 years, people haven't asked me that anymore.
I see.
And
Okay.
so many students at Harvard or at other places, they understand that in order to do biology well, you need a lot of mathematics, you need a lot of computer science. So
Right.
it has changed.
Did that start with Gregor Mendel? I mean,
No, so Mendel is a very, very important. So the history, of course, of modern biology, or a big part of it, was Darwin's discovery of evolution.
right.
So for me, the curious anecdote really is that Darwin was the last person to discover evolution by natural selection,
Right.
because at that time everybody was talking about that, and he kind of nailed it. And afterwards, nobody else could say, "Hey, I've just discovered evolution by natural selection." But before him, there was, of course, Lamarck, and
Right.
with him there was Wallace. There was
Hmm.
also this Patrick Matthew. So there were a bunch of people, all of whom used some idea of natural selection to explain adaptation or so. And the
Right.
one thing that Darwin then truly said that was new is that natural selection can give rise to new species.
Right.
But that nobody accepted. His followers didn't actually accept that afterwards. That took much longer.
Oh,
That
really? When did they start to accept that?
Yeah,
That
that was really the work of Ernst Mayr. So Ernst Mayr, a Harvard biologist who figured out the speciation, how natural selection actually gives rise to species.
and to do that, you had to know some about genetics, I imagine. And
Well, so the problem was Darwin never knew genetics. So Mendel's work, Mendel was an Austrian monk, I'm
Right.
sort of proud to say, and apparently he wanted to become a scientist, but he couldn't become a scientist because he failed botany twice, actually. He was very good in mathematics. So
Uh-huh.
instead, his backup career, his plan B, was to be a monk. And
Uh-huh.
as a monk in this abbot, he had time to do research. They had a garden, and in this garden, he did this piece. And he did like he started in genetic inheritance. So he discovered the foundation of all of genetics. And
Right.
his work was published in the Brunn Academy of Sciences, I think in 1865 approximately. And at the end of the year, the president announced nothing important was discovered by us this year. That was the summary sort of the Brunn Academy of Sciences this year. It
Right.
was not appreciated. And Darwin, who read widely, could have read it, but didn't. Darwin never knew about Mendelian genetics. Darwin himself believed in blending inheritance.
Right.
And Mendelian genetics is particulate inheritance. And so when that was discovered by evolutionary biologists, there was this crisis. And this crisis led for the first time to a mathematical approach, and that's called the neo-Darwinian synthesis.
Right. So, I mean, Mendel's work was an application of precise mathematical laws to a problem in biology. I mean, so genetics is a highly
Yes.
mathematical field.
And moreover, he had a certain expectation. He had a mathematical expectation of what he wanted to find.
Right.
And it
Now,
has been said that his data really didn't actually show what he wanted to see, but he saw it anyway.
right. Now, the thing about mathematics and science, there's this famous quote. You've given it in your talk at our conference, but it's very famous in the world of physics from the great physicist Eugene Wigner, and he wrote an article back in 1961, I think it was. Anyway, around that time, I think it was called "On the Unreasonable Effectiveness of Mathematics in the Physical Sciences or the
I
Natural
mean, I think
Sciences."
he writes in the natural sciences, but of course he means physics.
He means
He
physics,
means physics.
right? So, and this is a famous question, and it's very striking. I mean, I come at things from the physics point of view that physics requires very sophisticated mathematics, very abstract mathematics, surprisingly so. So, for example, everybody understands regular, counting numbers that you can talk about how many cows there are standing in the field or, but you have numbers like complex numbers, which have the square root of -1. And people who've taken some math in high school will know, what does that have to do with the real world? Square root of -1, or so. But it turns out that that's needed in quantum mechanics. You need to use complex numbers, and it's very strange because complex numbers were deeply studied in the early 1800s, at which time people thought they had no relation to the real world. Uh, but then 100 years later, you find that you need it in quantum mechanics. And this has happened over and over again in physics, that mathematicians study certain mathematical structures just because they're beautiful and mathematically interesting, but they think useless. And everybody thinks this is useless stuff. It's just beautiful math. And then much later, later, suddenly you find that this beautiful math is needed to describe the physical reality. And that's a big puzzle. So why is that? Why does all this very abstruse mathematics, why does nature make use of it? And so that was his famous question. So what do you think about that?
I mean, I think science itself cannot really give an answer to that question. And that's why that question is so interesting.
Yeah,
So for me, this is one of those questions that bring us into philosophy and that bring us into theology. And that somehow is a question that almost demands an answer of the kind, this is how God has set it up.
right.
But just to say that, yes, it's true. Sometimes mathematicians do things which later become useful in physics or so. But often it is also the case that the mathematical advance is really motivated by questions that arise in physics.
Right.
So I think there's a very strong cross-fertilization or has been between these two fields. And the same sort of is true also of computer science and I think now biology and other questions. I think mathematics is influenced by what would be the need of science.
Right. So an example. So your work, I'm looking at your resume. It's really quite remarkable. You've done work in evolutionary biology. You've done work on cancer, on both the spread of cancer and disease, how it develops in the human body, and treatment of it, um, cancer treatment. Uh, and to many people, that would seem um, strange, but it all goes back. A lot of what's the common theme in your research, both on evolutionary biology and on medical
Yeah,
research?
I would say the common theme in all of my work is actually evolution itself. Because in the medical areas, I have worked on viruses.
Uh-huh.
The HIV virus, for example, we gave a strong mathematical argument for the evolution of resistance of the virus to single drug treatment. And that argument led to the adoption of multi drug treatment against the HIV virus.
Right,
And so it was always the evolutionary approach. A virus comes into a person and then replicates and forms billions of viruses, and all of them are kind of different because of mutation and selection acts. So it is
right.
evolution, it's applied evolution. And the same is true of cancer. So cancer is an evolutionary process.
I
Cells
see.
get mutations, and then there is selection among cells that lead to faster replicating and more dangerous cells, and therefore also the study of cancer is applied evolution. And in evolution, I'm super interested in this question, evolution of cooperation, and cancer is also this breakdown of cooperation among cells.
I see. I heard a talk by you that you gave some years ago, and I had the impression, correct me if I'm wrong, that the game theory has a big application in
Yes, so
your
so
research.
game theory is a very interesting, it's a field of mathematics that was invented by the Hungarian genius John von Neumann,
Right,
working together with the Austrian economist Oskar Morgenstern in Princeton
right,
after the Second World War. And they invented a mathematical field with the aim to study strategic and economic decisions of humans.
right,
And so this is game theory, and game theory is an important part in economics, mostly with respect to human decisions. And then there was John Maynard Smith in Britain, and later also my PhD advisor in Vienna, Carl Sigmund, who brought actually game theory to biology. And they
right,
brought it to biology to apply these methods to animals, for example, or to cells. And now, with my work over the last few decades or so, we would say that game theory is everywhere in evolution whenever the success of something depends on what others are doing. So
right,
if the success of a cell depends on other cells,
right,
with game theory, so it applies very widely the dynamic of evolution. And
right,
an exception to that would be my success depends only on the shape of my body or my wing or something like this. And that would
right,
be the standard way to think about natural selection.
right. I mean, so for people who are not familiar with this field, game theory sounds like something that's not very serious, but it's very serious.
Yes, that's right. So
um,
when I was
it
very embarrassed when I had to come home to tell my parents that I'm now working on games.
right. I mean, so I games. So maybe as a brief explanation, game theory has to do with finding the right strategies. Many met games like the chess or poker and so on are very mathematical games. You have to do a lot of calculating, and so game theory is about, as I understand, is about finding strategies for winning in these games, and it applies certainly to evolution because you have a kind of competition among species. So there's a bit. It's a kind of a very
Yes, so,
serious
so,
game.
so yes, ecology. So that's called ecology. So again, that's completely correct. So in ecology, we study the competition of species, and that is exactly game theory
And
because
but
success.
also in cancer, and this is where I heard a talk by you, if my memory is correct, that in cancer treatment you have on the one hand the cancer cells, and then you have the body's immune cells, and then you have the medical the drugs or the treatments, and they're all, the treatments can kill the cancer, but they can also kill the immune cells.
Mhm.
And so, what is the optimal strategy in this three, or maybe it's even more than three-way
Mhm.
battle between the cancer and the treatment and the immune system? And that's obviously going to have game theory in it also, right? I mean,
Yes, I mean, game theory would also arise in cancer if cancer cells actually help each other. For example,
uh-huh,
they help each other to survive the attack of the immune system, or they help each other to find blood supply. And that would
right.
be an example of game theory in cancer.
So that gives some idea, I hope, to the people listening or watching, an example of how mathematics applies to perhaps unexpected places, mathematical analysis. Maybe we can get into, you talk about at some point. We're going to sort of follow the line of thought or treatment in your talk at our recent conference. So you talked about the indispensability of mathematics in natural science, and so maybe we can get into that topic,
So
how
the
important it is.
somehow the way how we got there was really ultimately we want to understand whether mathematics is something that brings us closer to God.
Right.
And so this is how I see the argument really unfolding. In the modern world, sort of it is a widespread view that the material world is the only thing that matters. And basically science studies that material world and explains everything.
Right.
And so you could say, a person could say, I'm not interested in anything other than the material world. I'm not interested in anything other than what science tells me right now or will eventually tell me.
Right.
And so I have the confidence that science gives the answer to everything, explains everything.
Right.
And now I would ask that person, if you think that science explains everything, why does science not explain mathematics?
Right. So the idea that science explains everything is, sometimes people call that scientism, that
Yes, it's science.
the only knowledge, the only reliable or real knowledge we have about anything comes through natural science, through
Yes,
physics and chemistry and so on. And so that's one of the major stumbling blocks people have in accepting religion, because religion is making truth claims that you can't verify using the methods of natural science. So the
yes,
idea that science is the only way to explain anything is a big problem.
that's right. So they might say, I don't need God, I have science. I
Right.
don't need God, I have evolution or something. I hear this quite often. So this scientism, as you exactly said, scientism or physicalism or materialism, they are related things.
Right. So tell us
Naturalism.
about materialism and physicalism.
So materialism is basically the material world is the only thing that really exists.
Right.
Physicalism is then, well, physicists, they seem to talk about more complicated things like a, a field and so, and so we have to add something to that material world to really cover what physics are talking about. So that's physicalism.
Or at least the physicalism is sort of a modern, souped up version of materialism, which says that matter is just what physics tells matter is as physicists understand it.
Yes, yes,
And
exactly.
that's the ultimate reality, just
Yes,
matter. Yeah.
yes, that's right. And so scientism is like this confident in science. So, and then these positions, they now get a pause when you ask them, where do you place mathematics?
Yeah.
And so let us now examine that. So I say science does not explain mathematics. What do I mean? So, for example, let's suppose a mathematician spends many years trying to prove something, say Fermat's last theorem.
Right.
And say after years, he says, I have a proof for Fermat's last theorem.
Right.
And then if other mathematicians check that proof, and if it turns out to be correct or so, then there's no physicist is needed to perform an experiment. So no scientist is asked, can you test whether that is really true? It is
Right.
just truth in itself. So physics is not needed to find truth in mathematics.
And it's not even very well. It's probably not even very helpful.
Yeah, it's not. It's even unclear in what sense it would be helpful. So then So physics or the natural sciences, they do not explain what is true in mathematics, what is not true in mathematics. But truth in mathematics exists and is independent of science. So there's something
Right.
that's independent of science. And now we can ask the other question: is if mathematics doesn't really need physics, can physics go without mathematics? And here the answer is absolutely no. Absolutely not.
Right.
So physics is this what you call the indispensability of mathematics, the argument, and this is the best possible science that we have right now. Physics and also biology in some fields is totally dependent on mathematics, and one cannot do it without mathematics.
Mathematics is really foundational
This is
in
foundational.
physics, and this is something that most people don't really understand. It's not just it's not just a matter of counting things and so on. If you ask what things are, the deeper you go. I mean, here I'm talking as a person in theoretical particle physics. The deeper you go and asking what is matter, what is this matter that the materialists are always talking about? The deeper you go, the more and more mathematical it is. So you might say, well, what's this stone? What's this rock that I'm holding in my hand? Well, it's made up of atoms. And okay, so and atoms are some material stuff. And you say, what's an atom? Well, it's made up of these electrons and orbit around some nucleus. Well, okay, and electrons a thing, and nuclei is that's material stuff. Well, and then you start saying, what's an electron? And as you go deeper and deeper, what an electron is basically, to a physicist, it's basically something that satisfies a certain very beautiful equation called the Dirac equation. And it has a certain properties that are mathematical. It has an electric charge, which is -1, and but it's basically just this mathematical thing. And so you find yourself doing what's you're no longer talking about stuff. You're talking about mathematical structures of things. And it's like it's mathematics all the way down. So that's hard to get across, I think, to the average person, because he looks at the world and says, well, what's this coffee cup? This isn't a mathematical thing. But the deeper you go, the more
So
you.
actually, the cup is a very mathematical thing because the only reason why my hand doesn't go through it is the electromagnetic force.
That's right.
And this is amazing. So there's a field that these fields reject each other.
That's right. If you start asking what causes this rock to be solid,
Electromagnetic force.
It's quantum mechanical.
And if you ask where is the mass in the cup that I'm holding, it's actually not. It's not in the. It's in the force field between the quarks. So the mass is made by the force field of the quarks in the nucleus.
Right. I mean, it's all when you start getting into, why is this table? People say, well, matter is this just stuff. I can touch it. I can see it. I can touch it. I can feel it. But what is seeing? It's all electromagnetic waves, and the thing is solid because of the Pauli exclusion principle and quantum mechanics and so forth. It's all mathematics, but people don't. But it's people don't see it.
So in some sense, I like to say this jokingly, but the story that modern physics is telling us about the universe is actually quite unbelievable, quite miraculous, even more unbelievable or as unbelievable as the story we read in Genesis. There's not much difference there. So we have to postulate dark matter, we have to postulate dark energy and all of those things.
Yeah, I remember my father told me an anecdote, and I have not been able to find it, but it was about the great mathematician, Irish mathematician, William Rowan Hamilton. And back in the 1800s, he discovered this mathematical structure, this algebraic structure called quaternions. And it got to be quite a sort of a phenomenon, like people in parties and soirees and would talk about, the Professor Hamilton discovered quaternion. It was sort of like superstring theory or the Big Bang. It was something that in social and gatherings people would talk about, but it was famous because it was useless. Quaternions were this utterly useless thing. And so if the story goes that this aristocratic lady once asked Professor Hamilton, are quaternions useful for anything? And he said, aye, madam, quaternions are very useful for solving problems involving quaternions. And but it turns out, and I had a friend of mine who is a philosopher, said, Well, here's an example of useless math, quaternions. I said they're not useless. It turned out in the 20th century that that very same algebraic structure is needed to describe the spin of electrons and other things in fundamental physics. So this useless math is actually very fundamentally important in modern physics, in particle physics. Anyway, a bit of a digression, but it just illustrates that how deep mathematics goes in the physical world. So getting back to what you were saying, mathematics is an example of a field of knowledge, things about which we know. In fact, maybe we know with more confidence and certainty than any other kind of knowledge. But it doesn't come from doing sort of scientific investigation. It's not empirical knowledge. It's a knowledge we get. The scientistic person is clearly wrong. It's natural science is not the only way to know things, because actually some of our most certain knowledge comes in a completely different way,
Yes.
as in mathematics.
And here I like very much what Augustine would have ordered knowledge like this. He would say everything we know about the material world is at best an opinion.
Right.
And mathematics he would sort of put under intelligible object.
Intelligible objects. And that's it gets to another question is, what are these objects? Like what are triangles, and what is the number pi? What are numbers? What
Yes,
is this? What are these physical objects? Um and this gets into the whole, and so that they seem to exist, right? I mean, people make discoveries, they learn things about the number pi. I mean, the pi seems to be a thing you can learn about and know more and more about, and yet it's not not material.
yes,
So it's a thing, but it's not material. So that sort of strikes against materialism, right?
yes, yes. So the interesting thing, this brings us to the philosophy of mathematics.
Right. So let's go there. The philosophy.
And
What is mathematics?
yeah. And before we begin with the philosophy of mathematics, I want to say again this Augustine, because I find it very beautiful. So an intelligible object.
Yeah.
Imagine you are sitting in a math class.
Yeah.
Imagine the professor explained something to you, something maybe about triangles or about numbers, and after some time you grasp it. Let's say
Yeah.
there's this moment where you understand it.
Right.
And in that moment, you don't need the teacher anymore. You know it by a criterion that you have found within you.
It's
You,
within.
yeah, there's something about it that is within.
Yes.
And, and it is not because of the authority of the teacher. It's not by the experience of the teacher that I now believe this. I believe it because I have understood it.
You're correct.
And so this is this criterion that you have within you to judge an intelligible object. And Augustine describes this.
Right. I
And
mean, an example of this, and I don't know. I've read a little bit of Augustine on this kind of thing, but not as much as you have. But how do we, when mathematicians are just talking with each other using blackboards, they might draw a circle, like the geometer might draw a circle on the blackboard, but that's not really a circle, right? It's bumpy and it's misshapen. It's probably it's not a perfect circle. You can't draw a perfect circle. They're probably in the physical world. You probably cannot have a perfect circle. And yet we know by looking at that picture on the blackboard, you say, oh, I know what you say. You're talking about this thing called a circle, this perfect
yes,
mathematical object. Now, it's not something he learned about by looking at the picture, because that's not a circle. It's only an approximation. It's not something that comes in through the senses, or especially the number pi. We don't learn about pi through our senses. It's somehow, as you say, it's something inside us. The light goes on and we say, I
yes,
understand you're talking about this mathematical object, which somehow we know about, even though it's not coming through our eyes or
yes,
ears,
yes.
right?
Yes, that's right. So therefore, mathematical objects, they really bring us to what is called Platonic form. So for me, this
Platonica,
is the first time I understand the idea of a Platonic form with this circle on the blackboard or the
right,
triangle. So the more I understand that the teacher is not talking about this circle, and the
right.
more I understand that the circle couldn't even be drawn, the more I understand the real thing.
The
About
real
what we
thing.
do.
And
And so
the real circle is not a physical thing.
that's right, the real circle, not a physical thing. And
The
so
physical one's not a real circle.
that's the Platonic. So now that gets us into the philosophy of mathematics. So
Yeah.
there would be the first position, there would be four, we can distinguish four positions in the philosophy of mathematics. The first one is called realism.
Mhm.
Realism is really Plato's perspective. And the realism would be mathematical objects are real. So they really exist. They are abstract and they are independent of human activity. So that's Plato's position. So then the next position is immanent realism.
Mhm.
So this is Aristotle's position. Aristotle always had to disagree slightly, at least, with his teacher, Plato. So he says mathematical objects exist. So he also affirms the existence of them, but they are in matter. Therefore, we call it immanent realism. So
Right.
when he says, for example, the number three is there is a pile of three books. There are three books on my desk. So that's the number three. And then there could be four windows, and that's the number four. And
Right.
so then Aristotle already didn't like infinity. So for him, infinity was not something that existed because he realized infinity cannot exist in matter. So he accepted that there could be an unending sequence of numbers, but there's no such thing as the infinite for Aristotle.
Right.
So this
So
is
to
immanent
him,
realism.
if you ask him what is a sphere, he would say it's some aspect of a spherical object like a ball.
Yeah, all
So here's a
Platonic.
ball. The ball is the real thing, and the sphere is just sort of a feature of that ball.
Yes,
Or
that's right. And if all spherical things in the universe were to disappear, then the Platonic form sphere would not exist
there would be nothing. There would be nothing left. Right.
for
So
Aristotle. So in the philosophy of mathematics, this immanent realism is kind of rejected
right.
because we really talk about infinity and we talk about many levels of infinity in a very meaningful way, and they cannot possibly be in matter. But in set, the concept of a mathematical set is not something that can be in matter.
Right. And as you know, to take examples, the square root of -1, even though it's useful in physics, it's not in matter in the same way as a round ball, the sphere is in matter, or
Yes, so,
the
so
number
immanent
pi,
realism
or
is typically no longer considered a very viable option in the philosophy of mathematics. So we have two other things.
right,
One is psychologism or conceptualism, and this is that mathematical objects exist, but they are in the brains of people. So mathematicians kind of have these things in their brain, and this is where we find them. So if
right.
we look for the existence of a mathematical object, we have to look in the brain of a mathematician.
Okay.
Again, this is not widely adopted anymore in the philosophy of mathematics, and Frege gave very strong arguments against it. And he
So,
said,
to give an example, if you say, what is the number pi? Well, you don't find it in the physical world, but you find it in the heads of
yeah, I
mathematicians
would have found it.
who are thinking about pi.
Yeah, that's right, something like that, yes. So
And
then
so
Frege,
it's something going on in their central nervous system.
yeah, something like that. So Frege says it doesn't really work for the following reason. Imagine the simple question. Let's take two large integers a and b, and I want to know whether there's a prime number between a and b. And then if psychologism was true, then that question would be an empirical study whether I can find that prime number in the brain of a mathematician.
Right.
So like a biologist would set out to find a species somewhere. and, and that is not really how truth in mathematics works.
Right.
So one does not deny the idea that mathematicians have ideas of mathematics in their head, but it's not about how you find truth in mathematics.
Right.
So the truth is established differently in mathematics and not as an empirical psychological study of what is in the brain of a mathematician.
Right.
So this leaves us with the last position, and the last position is nominalism.
Right.
So we have not rejected realism, we have rejected immanent realism, we have rejected psychologism, but we are now dealing with nominalism. So nominalism says, for the first time it says, mathematical objects do not exist. So this is anti-realism. It
Right.
denies the existence of mathematical objects. It says instead, mathematical objects are only names that humans have invented. So we have invented the name triangle, the name sphere, and the name three, and we talk about those names.
Right.
but there's nothing to which those things actually these names refer to. That's nominalism.
Right. It'd be sort of analogous. I mean, nominalism is used more widely in philosophy. So what is the color red? Well, red is basically whatever we decide to call red. So we see a red ball, we see a red horse, a red this, and then people can decide among themselves, we're going to call all these things examples of redness, but redness doesn't actually exist anywhere.
Yes,
It's just a convention. We
yes.
decide we could have this. Well, we could call both these things green, but some other culture might call this blue and this turquoise or something. It's sort of all made up and conventional names, right?
So then
Can I? Yeah,
the debate, you could say, in the philosophy of mathematics is still going between realism and nominalism. But I can give you an argument against nominalism, and that argument really works like this: that uh, all philosophers, also nominalists, accept that mathematicians know what they're talking about.
that
This is
mathematicians know
this
what
is how
they're
it
talking.
starts. So everybody agrees, mathematicians know what they're talking about.
Right,
And so when a mathematician says, I have a theorem, and other mathematicians then say, yes, the proof is correct, this is a statement about truth.
right,
But you have to accommodate in your worldview the idea that mathematics is really about truth, that there's some truth there. And
right,
then comes an argument from Frege, essentially, and from Quine, famous Harvard philosopher Quine, that in simple mathematical sentences, or in simple sentences, you are committed to the existence of those objects that you're talking about. So when, for example, when I say this flower is red, I may not really know what red is, but it's very hard to understand how the sentence could be true if this flower doesn't even exist.
right.
So I'm committed to the existence of the subject of this sentence.
Yes,
This flower exists. And so then Quine says in mathematics there are many such sentences, like 13 is a prime number. So
yeah,
I cannot really have it both ways. I cannot say that sentence is true, and yet 13 doesn't even exist.
right,
That's the argument against nominalism.
right,
And nominalists, they wind themselves out of that argument by saying there's a language of mathematics and a language of philosophy. And
right,
in the language of mathematics, they are committed to the existence of 13 because they say 13 is a prime number.
right.
In the language of philosophy, all that I'm saying is the sentence 13 is a prime number is true. I'm
Yes.
not committed to 13. That would be the argument for nominalism.
So is this connected to Wittgenstein's language games, or he talks about not really? I mean,
I
so
got
that but they're saying that this is all a matter of what your field of discourse is. In some context, you treat certain things as true, um, but that's really just sort of part of the rules of the game of what you're talking
so
about.
my argument against the argument of nominalism would be, but this is really almost outside, certainly, I mean, outside my real expertise. But I would say that if you ask, then what is the language of philosophy that you want to talk about? That language of philosophy has, for example, the language of mathematics in there, that is an object. But the
Right.
language of mathematics itself is a mathematical object.
Yeah.
So what I cannot believe is that you have a language of philosophy to cover every aspect of truth that does not have any mathematical object in it,
Right.
because everything for me is a mathematical object.
So let me ask you. So we're on philosophy of math, and we have these four positions. The two extreme ones being the most defensible. One is what's called mathematical Platonism or realism, and that says, which I tend to like you. Most mathematicians actually, in their heart of hearts, are mathematical Platonists. So mathematics, according to that view, is a real realm of objects. They're talking about real things that exist even if humans didn't think about them, they'd still be there. 13 would still be prime, and so on. And so it is, and it's a realm of these intelligible forms or objects. It really exists. Um, And then at the other extreme, it's all words, it's all names of things. But the only course in philosophy I ever took in college, because I'm very interested, is the philosophy of mathematics. I took a course in that, and I now forgotten most of what I was taught. But I remember there were two theories, and I don't know where they fit in these four that you talked about. One was called a logicism, that mathematics, and I think maybe Frege was a logicist. I'm not sure, but if mathematics is just logic, and there's really nothing to it. I remember talking to a biologist friend of mine, and and I was saying how there's this realm of mathematical truths, that there are these truths out there that we discover. We discover these truths. And she said, no, but mathematics is just logic, and it's just and you and it's not much to it. But what does that fit in? Is that I think most that's also not regarded as a viable theory now. That it's just
No, no, that is. So you could say, how do I build my foundation of mathematics?
right.
Is the foundation of my mathematics, do I use things like numbers and shapes and sets, or do I use logical operations, logical considerations? So I could do it in two different ways. And for me, ultimately, that's just a matter of preference, but it's the same. So for me, it's something that will be the same. So that is very meaningful. So the foundation of mathematics is logic, and Gödel, of course, is very important for the foundation of mathematics, and he is the greatest logician after Aristotle.
I mean, I read as what I do remember is the argument that mathematics is just logic. Is that it's a bit of what you mean by math and what you mean by logic. Some people would say logic is just a part of mathematics, and others say that. But conventionally, I mean, traditionally, logic didn't commit you to the existence of anything. I mean, you could say, if there's a mountain of gold in my front yard, then certain things follow from that logic. But you're not committed. In logic doesn't tell you what exists, what doesn't exist. It's just if then, there's certain. But in mathematics, we are, as you said, committed to certain things existing. Certain the numbers exist, the counting number. There exists a prime number greater than 100 is a statement in mathematics. So you're committed to certain things having some kind of existence. So which is really impressive. I mean, when you think about it, you're but the other one I wanted to ask you about is there's the field that the theory of math that it's just formulas. It's just formalism.
Yes.
The formalist school.
Yes.
I think Hilbert was a
Yes,
formalist.
that's a very important. So David Hilbert, one of the greatest mathematicians of all times, and he said the best way to think about mathematics, it's a rigorous method about, it's a game. He also used the word game. It's a
Right.
rigorous method, a game with rules of how to manipulate strings.
So you have symbols
Yes,
and then
you
strings of
manipulate.
symbols and rules.
So that was very important for him because he was very influential in sort of the development of algebraic geometry. And so before this, geometry was very much based on like an intuition. So you draw a line on the blackboard and then you make a point to it, and then you say, look, you can look at this. There's only one line that goes through that point that is not intersecting the first line. And so this was kind of a valid method in normal geometry. And then they realized this valid method lets you down often. So it would be much better to have a geometry that doesn't rely on these pictures that are in front of you. And he then developed exactly that. So for him, then geometry became something that was just about manipulating formulas. And he says, we don't have to call it point, line, and plane. I could also call it beer, elephant, and lamp, and I give you the same geometry kind. So that was a very important approach. And there was a famous professor of geometry in Germany at that time who insisted that he would teach his geometry class only in a completely dark room.
Wow.
So nothing could be drawn.
So as I understand it, this idea, at least as some people held it, is that mathematics is just about certain symbols, and from these symbols you construct strings of symbols which you call sentences, and and then there are rules for manipulating them, for manipulating these symbols, and the symbols don't have to stand for anything. That
Yes.
is, in other words, there is no mathematical realm out there that these symbols are describing. They're just symbols,
Yes.
and so that would be counter to the realist view.
Yes.
That's all it is.
Then
Yeah,
Hilbert was asked, okay, so mathematics is just a game. It is a game that has rules about manipulating strings. So does that mean it's an arbitrary game? And then he said, oh, no, that would be completely wrong. It is a game as given. It is completely determined. And this makes him again totally a Platonist.
this makes this was
This makes
Hilbert.
Hilbert a Platonist. This
Right.
makes the connection with Platonism. So the rules of that game are not sort of invented by us; they are given by something.
Right.
So the mathematical truth is fundamentally given by something.
Right. I mean, so if you teach the kid how to do long division, and you just say, here, you write the number here, and then you put another here, and you manipulate this and the right, and the kid might not know what he's doing. He's just following the rules you taught him. But there's a right way to do it and a wrong way to do it, and it has to do with the way numbers are. Right? I mean, there's actually truth in arithmetic. 2
Yes.
plus 2 is equal to 4, and your rules better reflect the reality out there. Otherwise,
Yes.
okay. So you're really back to realism and Platonism.
So I would say that this logic, the position on logic and the position on formalism is not at variance with Platonism at all. It can actually factor into Platonism.
It goes back into it. So we're back to this idea, which I think is very important, and is part of how mathematics leads to God, that there's this realm out there of mathematical reality that we discover. People have often debated, do we make discoveries in mathematics, or are we inventing things in mathematics?
Yes.
And I think most mathematicians and I think most physicists believe you're discovering things. You're discovering things.
It's a very strong sensation that every mathematician has. I have just discovered something.
So there's a part of reality which is not just reducible to physical science or to empirical science. It's real. It's also, and this I think you mentioned, it's unlike the world of physical stuff, which is constantly changing. The realm of mathematics is sort of eternal and unchanging.
Yes.
It's infinite. It's eternal. It's unchanging. It almost has some of the attributes that remind us of God.
So this is exactly where I want to go. So we are now confronted with this world of truth, because mathematics is about truth, unchanging, as you say. Because what is true in mathematics hasn't become true today. It was always true. So there's not a moment in time when something becomes true or goes out of existence. It's unchanging. And then we realized that these mathematical objects guide physical events. So the laws of nature are mathematical objects that guide unfolding in the material realm. So we are now developing a worldview where what happens in the material world is governed by something that is immaterial and eternal.
Eternal, right.
And for me, that's a big step toward God. And so if you accept this as the architecture of our world, usually then I would rest my case, because for me, you have made a big step toward God.
Right. I mean, in fact, I think the big stumbling block for many of my fellow physicists or physical scientists or scientists in general is that they feel that the things that they can sense or somehow they're closely connected with the things that you can sense. The table which I can rap on, this thing that I can smell, that's real. And this idea of God, this immaterial being who's not physical, they can't imagine or conceive of things that actually exist that are not physical. But once they begin to realize, if you're committed to science, if you're committed to modern science, you're also committed to modern mathematics, and that's this infinite realm of things that aren't physical. that are just as real as this table. I think that is crosses the Rubicon. It crosses some threshold. I think it makes it easier. Let me ask another question. So you talked about the psychologism, that the idea, which doesn't really hold up, that mathematical objects are just what's going on in someone's brain. Well, what about the idea that mathematical objects are ideas that exist in minds, and not reducing the mind to the brain, but a mathematical object is an abstract concept that is intelligible, as you said earlier. It's an intelligible form. It's actually something that needs an intelligence to grasp it. And this leads to what I think St. Augustine's view was, that all of mathematical, all this realm of mathematically intelligible forms, these mathematical forms, exist as thoughts in the mind of God.
Yes,
So they're not existing in a physical brain, but they have to have a mind. If something's intelligible, you're talking about an intelligence ultimately, and so they have to exist in a mind, right?
yes. I love this argument very much, of course. And in election philosophy, I once heard all of Western philosophy is kind of built on Plato. Whenever we look at developments in Western philosophy, we have to ask, where does this stand in relation to Plato? And typically, modern movements or later movements in philosophy, they accept some things from Plato but reject others. So most of philosophy can be described as taking away from Plato. And there are only a few philosophers who have actually added to Plato.
Uh-huh.
And one of the few philosophers who has added to Plato is Augustine. And he adds to Plato insofar as he finds a home for the Platonic forms. So for Plato, these Platonic forms, they existed in a Platonic heaven. And Augustine, exactly as you say, he thinks ideas, they need like a mind. So Augustine places the Platonic forms, the mathematical objects, in the mind of God. He finds a home for them in the mind of God. And so I find that very beautiful. So you could think as mathematics is an expression of the divine thought, and
Right,
this divine thought governs the material world.
right.
And that, I think, is a very beautiful view that brings together Christian philosophy and science without any conflict.
Both you and I know, are great admirers of Saint Augustine, and um, he has a mysterious, in one of his books, which I recommend everyone read. It's one of his early works, so maybe didn't represent his mature thought. It's called On Freedom of the Will, and there's a lot of philosophy in there. It's written as kind of like a Platonic dialogue with his son Adeodatus, and there's a lot of interesting philosophy, and he talks about mathematics a lot in there. And there's some really profound things. One thing that struck me when I read it when I was younger, and I didn't know what to make of it. It seemed he said, "Wisdom is number," and I thought, what does he mean by that? I think he says that. Maybe it was a bad translation, or I'm misremembering. But but I know you actually go very far in thinking that even the divine logos, or the mind of God God's thoughts are very much mathematical. Uh,
Yes, so I think that what I want to say is that not only physics needs mathematics, but all of science needs mathematics, and mathematics is ultimately the tool of every progress in every field of the natural sciences. It will permeate more and more until also all of philosophy will become mathematical. That's basically how I see it. And and another aspect which I find interesting is that if you ask a mathematician about beauty, then they would say, well, mathematics is beautiful.
right,
And actually, mathematics is indescribably beautiful. There's something amazing about the beauty of an equation or a symmetry or something like this. So how does that work? What does that mean? And again, going back to Plato, uh, what is beautiful is what is good. The good is beautiful. So
right.
he equates the beautiful and the good. And so for us, of course, God is good, but the good and the beautiful are the same. God is beautiful. So the divine thought must also be the most beautiful thought. And
A lot
therefore,
of
aesthetics is beautiful.
A lot of ordinary people, if you say math is beautiful, they're going to be astonished because that's the subject, maybe second only to physics, which most people hate. That is, you say, "Oh, I hate math. It was so boring." But um, but a lot of the things they think are beautiful, like music. Everybody thinks music is beautiful, or some music is beautiful, and it can't be, is very mathematical. All the rules of harmony and rhythm and so on. And another, even in art, you walk into a cathedral and you see the beautiful vaulted arches and all the complex geometrical patterns. That's mathematical beauty. And for those of us who like games like chess, I like to think of chess as sort of geometry come alive. Chess is a purely mathematical game, but to a chess player, a game of chess can be very beautiful.
Yes.
And so a lot of people don't see how mathematics is connected to beauty, but a lot of the things that they see as beautiful, even if, a touchdown pass following the football, following some beautiful parabolic arch, a lot of things we see as beautiful are really mathematical when you look at them closely. And so maybe for the mathophobes, what is it, mathphobes out there, we should point that out. But so
The
mathematics,
question really, if mathematics is so completely fundamental to everything, why is doing mathematics so complicated? It
uh-huh.
is complicated. So that's sort of an interesting question, and I don't think I have an explanation for it. But one attempted explanation is really this is a limitation of the finiteness of our mind. Something mathematics is something intrinsically infinite, and we'll try to put it into this finite, limited minds that we have now, and therefore it is complicated.
Well, some evolutionary, so I should emphasize you are an evolutionary, one of the top evolutionary biologists, but there are some evolutionary biologists would say, well, human beings are nothing but apes and our ape brain. How can you expect the brain of an ape to understand anything? Even Darwin had doubts, how this ape brain of ours could be trusted to understand. But of course, we think there's more to us than that. There's also a spiritual dimension, as you say, it enables us to maybe we should get back to this because this is something we haven't gone into from your talk. There's an argument against mathematical Platonism that you mentioned in your talk, which is that if there's this realm of mathematics out there, which is eternal and unchanging and not physical and not material, and if, as many of our scientific colleagues think, we are nothing but a physical object made of atoms, well, how can our brain, which is just made of atoms, how does it have any connect with this Platonic world of eternal, unchanging, mathematical, unphysical ideas? And uh, and that suggests, and so we can't really know about mathematics, but we do know about mathematics, which shows that maybe our brains aren't just a bunch of atoms.
Yes,
There's more to it.
that's exactly so. That's also what I describe in my book, Within, recently. So the idea, the challenge to mathematical Platonism, or all of Platonism, is that there is this Platonic heaven. This Platonic heaven has these abstract objects. There's no physical interaction between us and these objects. So how can we know about them? So
Right.
if you tell me something about a mathematical shape or so, then how do you know about it? How do I trust that we talk about the same object if we have never touched it, kind of?
You can't physically interact with the number pi.
Yeah, something like that. And so the argument really rests on the idea that all of causality is physical causality. So all of causality requires a physical interaction. So when you are telling me something about New York, I believe you because you have visited New York. If you have never been to New York and you tell me about New York and you have never talked to anybody who was in New York, how would I believe you?
Right.
And so it requires this physical interaction for any kind of causation. And I would want to say that these mathematical objects are also causally active in this world, but it's a different kind of causation. So for
Different
me,
kind.
mathematical objects cause events in the world.
Right. I know that some of my philosopher friends, they don't they don't see how the laws of physics, which are a bunch of mathematical rules and equations, they're not causes. To them, a cause has to be some physical thing causing another physical thing.
Yes.
how can this abstract equation cause anything? But they do. I mean, they
That's
do.
what I
In
want
a
to
certain
say.
sense of causation, they explain why things happen the way they do. I
I
mean,
think you have to expand your perspective of causation. You have to allow another kind of causation other
right,
than by physical proximity.
right,
And for me, this is already divine action.
right,
So I would say that this is what it is when we talk about creation. This is how the mind of God instantiates the material.
right. You can build, a lot of the physical world is built up of mathematical structure. You can go from mathematics to physical things much more easily than you can imagine starting with just some stuff and getting the realm of mathematics
Mm.
out of it. I think ideas to me are more fundamental than physical stuff. So the spiritual or the forms, the mathematical forms, the more fun. So I could go on forever. I wanted to talk about more about Saint Augustine, but we're running out of time. But I think we should mention that you wrote a pair of very interesting books. I read them both. I just maybe you can hold up a copy of them.
So
Um,
the first
the
book here is Beyond,
Beyond, and the other
and
one
the
is
second book is called Within.
Within. And I will say, as a reader, I think I wrote a blurb for Within. It's a remarkable book. It's almost unique. It's sort of partly a dialogue between two characters, but it's also has dreams and sort of philosophical discourses and reveries and so on. It's a sort of a journey of exploration in this realm um, of mathematics and forms and philosophy and God and the soul and the soul and so on. It's a fascinating book. I've never read a book like it. I'm talking about Within, which I read more recently. So I urge anyone who's interested in this whole subject of mathematics, its relation to science, how it leads to God, and so on, to to buy these books, and because it's very rich. I learned a lot of philosophy and a lot of theology from reading these books. I learned these from a mathematical biologist. So thank you very much, Martin, for being on our show. Those who are listening and not watching, one of the books has the titles are very simple. One of them is Within, and the other one is Beyond. And they're written by Martin A. Nowak, Nowak. Maybe I should have spelled your name because not everyone's watching. Martin Nowak of Harvard University. Um, Thank you very much for being on the show. I wish we could talk for hours and hours about this stuff.
Thank you so much. Thank you for having me.
Thanks for listening to this episode of the Catholic Scientist Podcast, sponsored by the Society of Catholic Scientists. If you enjoyed this episode, please consider subscribing. And you can also show your support by donating to the Society to help us produce content like you just heard. You can donate by going to our website at catholicscientist.org and clicking on the donate button. You can also find other useful resources, articles, and videos on our website.